Hi, I'm Florian Stuckmann, Sales Application Physicist at SunNuclear. Today's paper focuses on correction factors and output factor measurements for small fields with our diodes SunSILICON and SunSILICON P. The question is, how large are the corrections we need to apply and what determines them? The study, which is led by Andreas Schönfeld, combines measurement data from 4 different sites with full XNRC Monte Carlo simulations. So that gives us 2 views of the same problem. First, we have the measurements, which are showing how the detectors behave, and then the simulation reveals what drives that behavior. So before looking at the results, we need to understand what is being corrected. A detector that is not perfectly water equivalent can perturb the radiation field, and the magnitude of this perturbation depends on energy and field size. The field output correction factor accounts for that effect, and almost every detector requires one in small fields. The authors therefore created detailed Monte Carlo models of both diodes. As shown here, they contain the same silicon chip, while SunSILICON P includes an additional shielding layer around the active volume. Then the LINAC heads were completely simulated by XNRC, and the dose was stored in water and inside each detector model to calculate correction factors for field sizes from 0.6 to 40 centimeters. The simulated responses were then compared directly with measurements, and the final comparison validates the models used in the study. Okay, so let us look on the results and let us start here with our SunSILICON. Figure 3 here overlays measurement and simulation across field size for 6 and 10 MV with and without flattening filter. And as a reminder, dosimetry protocols state that the detector is only usable for output factor measurements as long as its correction factor stays within 5%, so from 0.95 to 1.05. Luckily, every SunSILICON result here stays inside this window from 0.4 to 10 centimeters, its full rated range. From 0.6 centimeters upwards, the correction deviates by no more than 2% from unity. The agreement between both methods is equally strong, with a root mean square error below 0.002. So this is not a Monte Carlo result alone. 4 independent measurement data sets clearly confirm the same trend. Okay, now let us look on the SunSILICON P, the shielded sibling, which shows a different pattern. Here we see figure 4, which extends the field size range up to 40 centimeters. Below 2 centimeters, the correction rises sharply as the perturbation from the shielding becomes visible. But beyond that, the behavior changes completely. From approximately 2.5 to 40 centimeters, the correction remains within roughly 0.5% of unity. The reason for that behavior can be seen on the next slide. So figure 5 takes us here from observation to explanation. Instead of showing only the total correction factor, it separates the individual perturbation components. So what we're seeing right here, the circles represent silicon's fluence perturbation combined with its stopping power ratio to water. And this component increases with field size because silicon overresponds to the low energy scatter that builds up in larger fields. On the other hand, we have the triangles, which represents the housing perturbation. And for unshielded SunSILICON, this remains close to constant. For SunSILICON P, however, it follows the silicon curve in the opposite direction. So this opposing behavior is intentional. The shielding was tuned to compensate for silicon's large field overresponse. As one component rises, the other falls, leaving the total correction factor almost unchanged. And this is why SunSILICON P remains so close to unity out to 40 centimeters. So the practical conclusion is clear. Across their full rated ranges, both detectors require only small, predictable corrections, and the Monte Carlo models explain their origin. In SunSILICON P, the shielding is not simply an extra layer, its housing perturbation is designed to counterbalance silicon's fluence perturbation. For full clinical validation of both detectors, see our companion clinical evaluation paper. The next abstract we will discuss will continue with a different application, how SunSILICON behaves with electron beam dosimetry.